Hello everyone, my name is Yunli Zhang and today I want to talk about my final project about the stellar blend image classification. First of all, I will talk a little bit about my content. It will be about an introduction on the dark matter, gravitational lensing, micro lensing, ZTF wise field of view survey, disambiguate single stars and blended stars using machine learning methods. And then I will talk about my research methods about data sets, normalizations, technique, data embedding methods, visualization of the data and the data embedding, model benchmark. We'll talk a little bit about uncertainty quantification. And I will show the results and the discussion about the normalization, visualization, and data embedding as input to model benchmark, and accuracy and time to solution. So it will be a single stars versus binary system and versus line of sight and multi-class classification problem. And then will be a model comparisons. So first of all, I will give you a brief introduction about the research background. In 1933, a Swiss astronomer proposed the concept of the invisible matter, which he termed Dunkel matter, or popularly known today as the dark matter. Gravitational lensing is simply put, gravitational lensing is the deflection of light by the gravitating mass. It occurs when a massive celestial body, such as galaxy cluster, creates enough curvature of space-time for the path of the light around it to be visible band. And now I'm going to talk a little bit about the multiple light paths of the single lens supernova. So the dark matter is the invisible matter, and the gravitational lensing, so we can take the curvature of the space-time for the path of light around it, and micro-lensing properties cannot be measured without spatial compensation. So the stellar blends are typically disambiguate through the expensive method. For example, we use the spectroscopy, space-based telescopes, high-resolution ground-based telescopes, and many surveys generate low-resolution sky images like the ZTF survey, HSC survey, and this Rubin Observatory coming in 2024. I think currently they postponed it probably 2026. 2026, I'm sorry. So we want to automatically detect the blends from these low resolution images. Then I want to talk a little bit about the machine learning models. The classification feature base use the color and morphological information like decision trees, neural networks, and random forest. The CNNs were demonstrated for star-galaxy separation with competitive performance to a conventional random forest classifier. The neural nets tend to poorly quantify their own uncertainty, leads to overconfidently extrapolating on data. And in the automated classification pipeline, one decides to detect the low confidence prediction for possible human intervention. And moreover, the Gauss process are also particularly attractive because they can support fully Bayesian inference. Basically, it can give you the uncertainty quantification, which traditional machine learning model cannot offer. I will skip the literature review and talk about the scope of our work. This work focuses on the ZTF survey images. Basically, it is extremely wide field sky survey, and due to the data volume collected, there's the opportunity to extract information out of the data. One possibility is the identification of the step blending. So basically there are three different scenarios. First is with single stars, and more stars look blending together in the image. It will be a binary star or more than two stars blended. So it could be binary classification problem between a single and blended star, or a multi-class classification problem between the single, binary, and more than two subblended scenario. So information about stellar blends are important to study the dark matter through the gravitational lensing. So this will be our data set. The dataset consists of the more than 27,000 one-channel binary class images of more than 15 single stars and more than 12 stellar bands. Additionally, the stellar bands comprises two classes, more than 7,000 blended stars and more than 4,000 binary stars. So it could be two binary classification problem, or it could be multi-class classification problem. And you can see that three classes are hard to distinguish visually. And then we take care of, we are looking at the pixel values. We found that only one realization of more than 27,000 stellar bands images are negative pixel value, and one out of this is very small. Though it is worth considering the physical meaning of this single with negative value, we treat it as a noise. So we do the distribution of the log mean pixel cross images and log max pixel cross images. We find out that this distribution. Based on this, we we design normalization technique to the data. And then I want to focus on about the data embedding techniques. Additional to the pixel-pixel normalizations, we further consider the following embeddings: the PCA, TSNet, and NewMap. We can see that for PCA and TSNet, it's very hard to tell the difference between the multi-class and the single star cases. Basically, the data point blend together, and for TSNet, the same thing happen. For NewMap, basically we cannot tell which one is which. But however, for the supervised NewMap, the train data separate perfectly, I would say, and the test data also quite separable. It is much better than the PCA TSNet UMAP. So in the following study, we will focus on the supervised UMAP data embedding technology as the data preprocessing. Now I want to talk a little bit about the benchmark results. The following models are the top performing. So the KNN classifier, decision tree classifier, multi-layer perception classifier, ResNet 18, and random forest. So first of all, we check the classifier without data embedding and normalization. We found that the KNN gives us the best accuracy is about 70%. The ResNet 18 also give up around 70%, and the multi-layer perception give the lowest accuracy is about 60%, and most of them are between the 60% to 70%. For multi-class classifier, which means three classes classification, without data embedding, we find that all accuracies drop slightly. For the KNN, it dropped like 4%. For the ResNet 18, it dropped about slightly smaller, about 3%. For the rest, they all dropped. Most of them lower than 60%. Some of them lower than 60%. But now we want to talk about the effect of the data normalization. We have four types of the normalization technique: log local, log global, local, root global. And we find out that we're considering three techniques: machine learning method, decision tree, deep neural network, convolutional neural network. And we find out that for decision tree, it doesn't change a lot. Go through it increases slightly, but it does not increase significantly. The log local give us the best results that increase like 5%. It is significantly improvement. But for the DMN, basically it does not change significantly. It even drops slightly for local, but for the root global, it increased like 3%. For the CNN, it increased significantly with the data normalization method, especially for this root global method, it increased from 63 to the 79. And now I want to talk about the effect of the data embedding and the training ratio. So now we use the models with data embedding. This is the binary classification. This is multi-class classification. We find that the KNN give us the best results. That result is close to the 80%. Then ResNet 50 also give ResNet 18, ResNet 50, and ResNet 155 also give us very good performance. And the decision tree is 78%. Random forest is about 80%. Multi-layer perceptron more than 79%. And CNN classifier more than 79%. And for multi-class classifier, KNN drop about like 2%, more than 2%. Decision tree drop slightly about 2%. The random forest drop about like 3%. Multi-layer perceptron drop about 2%. CNN classifier surprisingly does not change, and ResNet 18 drop 3%. ResNet 15 drop more than about 3%, and ResNet 155 drop about more than 1%. So basically, we can we can see that it does not change a lot for CNN, but for the ResNet, it doesn't mean the more complicated model will give us better results. It could be due to the low resolution of the images. So we can see that the features of the images are not so many because the resolution is very low. So it's only 100 pixels for each images. So we cannot see the advanced the advanced model give us a much better performance. And surprisingly, the KNN still give us very good performance. And then we talk about the accuracy of machine learning model with increasing. Sorry, this is a type of training ratios. So this means that the training ratio increased from the 0.1 to 0.8, so 0.10% to 80%. We can see that for the decision tree classifier without embedding and random forest without embedding, it does not change significantly as the training ratio increases. For the KNN method, it steadily increases as the training ratio increases. For the decision tree, KNN and the random forest with data embedding, we can see that the accuracy keep going up as the training ratio increases. Especially for the multi-layer perceptron with data embedding, it increased from about 64% at 0.1 training ratio to about 79% at 0.8 training ratio. So if the 0.9 training ratio, it goes even higher. So this proves that the data after embedding, it will be more sensitive to the training ratio. Now I want to talk a little bit about the following work. It will be uncertainty quantification, because the classical machine learning model cannot do the uncertainty analysis. Like the CNN, which is very powerful, and the ResNet, the multi-layer perception, they cannot do the uncertainty quantification, and it includes the data uncertainty and model uncertainty. Basically, it means that it does. If we consider the three scenarios like single blend binary cases, if we drop in this domain, it will be like uncertainty domain. However, if we use the Bayesian neural network, it can apply to study the uncertainty of deep learning, because it can give you the Bayesian inference, statistical inference, which cannot be offered by the traditional machine learning model. So it could be a next step. Thank you very much. That's everything I have for today. Thank you.